Chairman, dear colleagues, it's my pleasure to be here. I want to thank the SAGES Program Committee to allow me to give this presentation. Nothing to disclose out of funding from the European Union for the Vector project, which I will illustrate later. So when we deal with these actuators for controlling the instrument in endoscopy and in laparoscopy, we have the problems of power consumption. They are bulky and difficult to be embedded in miniaturized devices. So we need this kind of solutions or others that are the one we are looking for. These are just some examples, you know most of them. And when we deal with this use of magnetic systems for guidance and for anchoring, we have to think about heavy and bulky instruments. As you see here, this is the neo-based system for stereotaxis. You see the two bulky magnets here, or something much lighter as this one or this one for anchoring the gallbladder. And this has led to the studies that you probably know very well from Scott, mainly from Scott and from Olenikov, the use of these magnetic-driven instruments for minimally invasive surgery with different functions. And maybe could be a bridge to reach the pure nodes we are looking for, but not yet is here for us. So there are limitations. These are the three main. The magnetic forces change with distance. This is a big problem. And moving large external magnets can create a lot of problems in high precision movement. Third one, if you use these bulky magnets outside and you have a movement and inside you have graspers or trokers, you can damage the bowel or the structures. So it's a matter of safety for the patient. So we are looking for different solutions. This is the European project I'm partnering of, and this is the opportunity to also to thank the group from Dario, who is doing the engineering part of the project. Stay out of all the system, just have a look at this robotic manipulator for the external magnet, which is here. This is what you can see when you move the magnets inside the pig. I want to ask you to pay attention to the monitor. In a while you will start to see the capsule we are developing. It's an active capsule inside the lumen. And this is how the magnet has moved from outside. And you see this is the pill moving inside the bowel. You see it's not stuck to the wall, but just floating and moving up and down with tiny movements that you can regulate by the use of this magnet. But more, and I go forward just to save time, you see I think it's rather clear how you can move very tiny the instruments. This is always looked from a conventional endoscope just to, for saving, sorry. Go ahead, please. And what is funny is that you can drive this with a simple toy from my son, playing with the PlayStation. That's it. So when we go to this magnetic internal mechanism, we couple to the external magnet an internal magnet, a motor that can move the pill. Just to simplify things, because it's a lot of engineering, but it's not my field. And it may be easier to understand for everybody that the magnets are not interfering with the motor. And the design and the manufacturing at the moment is, this is the size, but next prototype will be 12 millimeters in diameter. That means that you can put it in a regular trocar. And the accuracy of the movement is about 2 degrees of angle, so very tiny movements. And this is a very rough initial movement of the camera here. Maybe I can click on that. Thanks. If you go to the next step, maybe it's clearer how it works. Can I? I don't know how to click on the. Okay, thanks. This is very rough experimental setting you see, but it's working very tiny, moving up and down, right and left. No? Please. The other. Anyway, maybe I can go forward to save time. Is it clear this way? How you can move the instrument? just with external magnet and internal motor. It's not working. This is the image you can have in this experimental setting. You have only 4 LEDs in this very first prototype, so the light is not as good as we would like. And this is an ex vivo test. You see the pill can identify easily these targets, and this is again the movement seen from the conventional endoscope. Next. This is the movement on pictures. And next, this, can you click on the 2 slides on the, no? Sorry for this, but I don't know how to. Also the other one. Do I have, no, this is on the Mac. This is the, again, the camera, which is wireless, moving inside the gastric cavity, no? And the other one is the vision from the camera. Anyway, a little bit of confusion, but I will try to go to the conclusion because I'm already running out of time. More, this is other possibilities. You see that there's lights. This is a chance to move the final magnet out of the pill so it can move more and more in the abdominal cavity. And with adding other possibilities like this one, this is a hybrid locomotion using motors. Just to conclude, maybe you should click on the 3 video clip, please. You can see how it is possible to, you could see how it is possible to let it swim and look around. I think the lower one is rather clear, and you see it's a very precise movement. So you can look around in the stomach, for example, filled by half liter of water, and have a real gastroscopy by a capsule which is swimming. I think this is enough for the time I had. I had some additional points, but I thank you very much for your attention.